All right. Good morning, everybody. Thank you for joining us. I apologize that my camera isn't working today. I'm Heather Kotula, President and CEO of Access Innovations, and I'm excited about this webinar today. It's a jam-packed webinar, and there's going to be a lot to learn. And I know that Margie's ready to get started, so I'm going to turn this over to Bill Kasdorf. Thank you, Bill.
Yeah, thanks a lot, Heather, and hi, everybody. I think this is going to be a really interesting and important webinar for folks because it's addressing one of the things that everybody seems to be obsessed with these days. First of all, AI, but also how the heck can you trust AI to not hallucinate, to not, to give you reliable results? And this is where using knowledge domains is such a useful tool in this. So I'm going to basically just introduce Margie. There she is, a highly respected expert in taxonomies, really for years and years. Taxonomies, metadata, data science. Her groundbreaking work has earned her numerous awards, and she's actively involved in standards development, having contributed to a whole bunch of key initiatives. I'm not going to read all these numbers, but all the way back to Dublin Core and DOI and credit, et cetera. She's been a major force in including NISO and ISO in terms of developing standards around data science. And she's the founder and chairman and chief scientist of Access Innovations Incorporated. So I'm not going to take up any more of her time because she's got a lot of slides to get through. So Margie, it's over to you.
Thank you, Bill. Actually, there's only 62 slides.
Oh, only 62.
Yeah, but
that's one a minute. Less than 1 minute. Less than a minute.
That's
more
true.
than 1 minute.
But let me just share my desktop and then share the slide, and I'll play from start. Oops, come on.
That looks good.
What we want to talk about is making AI behave, and I've put closed captions on the bottom so we can see exactly how AI is behaving for all of us during this presentation today. Certainly better than it used to be. In particular, well, here's the abstract, and Bill just went over this, so I'm not going to do that again, but we are all getting a daily deluge of all kinds of stuff about AI. I got a really good post this morning from someone on LinkedIn that said, well, I used Copilot to do it. And Copilot has been inserting itself into my Microsoft every time I try to boot it up. It doesn't do it on Windows 7, but it's certainly pervasive on Windows 10, I've noticed. And the headlines are all over the place, somewhere from nuclear war coming up and human extinction because of AI. Oh, come on. Is this the new Y2K that everybody was so excited about? And then it turned out to be nothing much. And lots of news about people, particularly the big companies, rolling out all kinds of new tidbits every day for us. And I gave a talk in November, which Bill and I cooperated on. And man, I went to work on this kind of stuff, and it's become even worse. So, and it's everywhere. We even have things where this person was talking to their loved one, their mother, and having an experience with them using AI to have a chat. Ridiculous. The challenge is that we don't know what's lurking behind that AI, the different models. They're all a little bit different, and we don't know what's lurking there. And that's a little scary because we want to be able to protect ourselves, our companies, our own information, particularly our intellectual content, our IP. And so knowing how to do that, or at least finding some ways to do that, while trying to keep do-gooders who are trying to regulate it before we know what the full possibilities are, is a little scary. The balance is really hard to maintain. You already saw this, you know who I am. I do have patents in this area, and I am convening now the ISO 25964, which is the international standard on controlled vocabularies, with a wonderful, wonderful group of people. So what people are often saying is that large language models are not only going to mirror, but also magnify any problems with the data sets, the problems that many organizations don't even know they have yet. So there are certainly data problems themselves, which come to the fore when you're putting this much additional power from the software systems onto them. But it also amplifies any hidden biases as well as gaps in the content. And that's a real danger to us all. We don't quite know how to handle that because we don't know what's there. You know, you can't, you drive down the street and you say, what used to be there? It's now been leveled, the building's gone, and what was there before? If it's missing, it's hard to identify. So what I want to cover today is some definitions first, and there's quite a few of them, but we have to do that in order to have us speak the same language. It's all of these fields had a lot of people speaking using the same terms, meaning different things to begin with, and now it's becoming a Tower of Babel. So we need to be careful. And so I want to go over the definitions. Most of the definitions that I'm presenting are from standards. So they're consensus agreed, and it's a good place to go and look for a real definition, as opposed to just a quick Google search. I want to do a quick review of the options that we have, realizing that it's a moving target from day to day. Then I, of course, want to talk about why taxonomies might work with large language models, where they fit. I want to talk about some available knowledge domains, and actually I want to talk about 3 approaches, not 2, and then sum it up. It's also important to talk about what we're not going to cover, because it's an incredibly big cover, a big topic. I mean, it's clear that you can do a ton of stuff with videos, and it's fun to do them, but we're not going to talk about that. We're not going to talk about the effect on politics and elections and other recent sensational things that come out from people playing with AI and getting it to do ridiculous things. I'm not going to cover all the tool sets because that also is a moving target and very, very fast moving. There's also a lot of new regulatory actions coming up, particularly out of the European Union. I'm not going to talk about those. I'm not going to talk about how you program this, and I'm not really going to talk about business cases either. I could talk about all of those. I think they're exciting topics, but that's not the topic for today. Today, we're going to talk about making AI behave with some things like controlled vocabularies. So according to the NISO standard, the Z39.19, a controlled vocabulary is a carefully selected list of words and phrases that are used to tag units of information, and it doesn't matter what the information is, in order to describe their content. So they are content related, and they are selected and managed by experts in a particular field. And they're done that way to ensure consistency and precision, both on the indexing side, or the tagging as the data goes into the system, and the retrieval, or what happens on the search side when you're getting stuff out. All controlled vocabularies are domain specific, which means they have to do with a particular topic. And that's important because the same word can mean different things in different areas. Take, for example, mercury. Mercury would, in some topical areas, be a element. In others, it would be a planet. In some, it would be a kind of car. It could also be a god. And so what do you mean by mercury? You either have to disambiguate it, or you have to say this controlled vocabulary is domain specific. Oh. You can probably hear that, but I don't know what's happening. There we go. So another way to define a term that's closely related is one of the kinds of controlled vocabularies is a thesaurus. A thesaurus is controlled and structured and represented by terms, but it has the organization of relationships between the concepts that are made explicit. And preferred terms, the ones that you want to use as the main term or the primary term, are accompanied by lead-in entries for that term. And then they also have the synonyms and quasi-synonyms listed. In fact, in a thesaurus, you have the hierarchical display, which is the broader, narrower terms in a listing. You have equivalents or synonyms, and you have associative or related terms. And those play a very active role when we get into things like ontologies and knowledge maps. They are structured. That means that somebody has put together a record about them, and it organizes concepts and facilitates the access to information. So what you end up with is a standardized terminology and relationships between all those terms or the concepts, their synonyms and their quasi-synonyms. So it's an important concept to understand what a thesaurus is, because from that kind of organization, whether you want to call it a thesaurus or not, a whole lot of other things spring. This is an example of a thesaurus. This is in the Data Harmony software. This is going to get old. And on the left-hand side, you see the hierarchical view. So it's broader, narrower terms listed. So under science and technology, we have mathematics, and then we have natural sciences. And under that, we have things like biology, chemistry, or earth sciences, and so on. These can be rearranged in different areas for different subject needs. On the right-hand side, you see what I call the term record. And that is the term itself, its broader term, and it can have more than one, a narrower term, status, related terms, synonyms, and this particular example is a newspaper thesaurus. So there's all kinds of additional information about the things that you might want to have in news. So you can put any kind of additional codes on it and so on. It's a really basic building block. A taxonomy, when a lot of people talk about taxonomies, it's the popular term these days, but it means a lot of different things to different people. It can mean a thesaurus or other kinds of controlled vocabularies. It can also mean just a really simple list. It can mean a way of speaking, but according to the standards organization, it's a structured and hierarchical representation of concepts or terms within a specific domain. And it's organized to show the relationships. It's just the hierarchy. It's just that now we often talk about it interchangeably with thesaurus and ontology. But as we get more into AI, we need to be a little more specific. So I just showed you a hierarchy on the left. Here's a hierarchy on the right, also a hierarchy. This is not, some people might call that a knowledge graph or knowledge map, but it's actually just a hierarchy. And here's a couple of other examples. The one on the right-hand side is a radial graph, but you can see that in the very middle, it says all about cocktails. And then it talks about how those cocktails can be used, and then more and more specific in the drinks as it goes out along the radial graph. This is just a display. It's just a way of looking at a hierarchical display or a taxonomy. So with those definitions behind us, I wanted to talk a little bit about what the steps are to implement a taxonomy into a generative AI model. Generative AI, large language model, not the same, but terms are used interchangeably. ChatGPT, OpenAI, there's all kinds of them, and they have the same kind of problems that we have with defining how we define a taxonomy. So the first thing you do when you're defining a taxonomy is identifying the key steps, the key concepts and categories. It's kind of this big heap of terms or concepts, or it's a heap of concepts with varying names, which we want to structure into groupings. those groupings are the categories or the classification system, and then the relationships to each of those concepts will go across those different hierarchies so that you can form what we call related terms. And giving those related terms means that you can build, for example, ontological relationships and knowledge graphs. Once you have all those terms and have thought some about the relationships, you can put them into a structure, kind of a hierarchy. The hierarchy is worthless for search, except in navigational browse. It is not anything more than a convenience, both for the person who is trying to do some discovery and for the person who's trying to organize a lot of terms together. So you want to group them together so that you can deal with them more easily. And the bigger the domain, the more important that becomes. We want to define those relationships between the categories and capture the connections. We call them nowadays semantic connections, but almost every place you say semantic, you could use the word instead, and you'd get the same kind of meaning. After we've kind of organized the concepts, then we collect the data. We want to have the data that's relevant to the particular domain, and then include documents or articles and all other kind of sources. And at this point, most of them, for most cases, really need to be textual. So we need to reduce them to text descriptions. And you say, what about videos? And videos is a different talk. For the moment, what a lot of people are doing for YouTube videos and so on to index them is taking the text layer, the transcription, and tagging those. That's fast, well-established, highly accurate. Working with videos to create new things and identify things that are similar is a whole different kind of process than what I want to cover today. Anyway, now that we've got our data collected, we need to clean it up, remove any noise, and make sure the formatting is fairly standard. For most of these large language models, you do not need to convert it to a well-formed XML or anything else, but you might want to remove stuff that you don't really want, and look at how to make the data as cohesive as possible. And then the next thing we do is annotate that data. And to me, I'm mostly annotating it with taxonomy labels or text labels from that structure that we worked on in step 1 above. And so we can do it all the way to the paragraph, image, and figure level. And that means that you have very discreetly tagged information. And once you have it discreetly tagged, then you can tag the generative AI model. If you dump it into a system or you add it to a platform before you've tagged the data, then you have to do a kludge job to go back and tailor it later. And it's much more costly than if you had done it in the beginning. And also you are not able to leverage your data in quite the same way that you could if you'd done it from the beginning. So when we train the generative AI model, you need to choose one or create one, but most people are going to choose one. There's a lot of them available on the market, and they're using generally a transformative architecture. And then we've got that annotated data set, and we're training the AI model on the annotated data, which means that you've got a clean, clear data set to work with. That allows the model to learn the relationships between the textual input and the taxonomy categories, which is very, very helpful. Means that your navigation schemes, for example, can pop right up when you get to that point on the search interface level. You can also incorporate the taxonomy into the model's interface so that after you've trained it, and you've integrated the taxonomy structure into the generative AI model's inference process, then when generating the text responses, the taxonomy is going to help guide the model's outputs. And you can constrain the generation process, or you can leverage it, depending on which way the questions or queries go. Once you've done all that, then you have an existing trained data set. You want to evaluate and perhaps iterate it, look at the metrics that are relatives, look at the accuracy and coherence or relevance. All those things can be statistically collected. And you could also get feedback from the users and from domain experts to identify areas that you think are ready for improvement. Using those domain experts, also known as subject matter experts, is a really good way to tailor and refine the model. And you iterate it then, making adjustments as necessary, and then you're ready to deploy it. And you can deploy it in the production environment or as part of a application that you're spinning out. It is prudent, particularly if you add more data on a regular basis, which you really should to keep current, to keep monitoring the system's performance and the interactions so that you gather data for further refinement and optimization. And it is true that as you look at this model, it's important to collaborate between the domain experts, the data scientists, and the AI engineers so that everybody's speaking from the same page, speaking the same language, and has a common goal. Okay, there's a couple of other terms that I talked about as I went through that. One is the knowledge domain. And that's a specific area or field of knowledge. So it's one of those subject domains. It's interesting that different bodies talk about their stuff, even if it seems like exactly the same stuff, in different ways. We have two clients, well, we have more than two, but the American Association for Cancer Research and the American Society for Clinical Oncology both study cancer. But one is a research organization and the other is dedicated to clinicians, people who are working to help you cure your critters. And so the people at AACR talk about the neoplasms. They're a research organization and they're going to talk about those things from that point of view. Whereas the people at ASCO talk about them as cancers. Well, it's the same subject area, but the basic subject term is so different, they can't use the same taxonomy. The way they think about it is different. And of course, I said I wouldn't talk about politics, but if you talk about the Democrats on one hand and the Republicans on the other, or you read the New York Times and the Wall Street Journal, sometimes you think, is that the same? Are they talking about the same item, the same law, the same regulation, the same problem? Because they talk about it so very, very differently. And those are extreme examples, but there are tons of them all over the place. It's why there's so many organizations for different topics, because it's like-minded people and they want to get together and talk with people who think like they do and talk like they do. They have their own vocabulary. So what we've tried to do with knowledge domains is build cohesive and organized bodies of knowledge that have a scope and a boundary. They can vary in size and complexity. We built one on COVID in the early days of COVID, which we gave away to all our clients. And it started out only 57 terms. It's much bigger now. JSTOR, which covers a lot of archival materials for journal publishers, as many of you know, is 57,000 terms and available to index large and diverse corpus of information, as is the Library of Congress, which has 208,000 or so terms. So when you talk about knowledge domains, you're looking at things all the way from quantum mechanics to medieval literature. We maintain a little system called the Taxo Bank, which lists about 2,500 different vocabularies that are available for reuse. And They're everything from the ones just listed here to one on sail making. There's another one, belly dancing. So they're highly variable taxonomies, but each discipline or subdiscipline has its own theories and methods and research transitions, traditions, and it's really interesting how they talk differently about the same topic. Always a taxonomy or a knowledge domain is a way to build a framework where you can understand and investigate phenomena within specific areas, and they represent all kinds of different people. So these are just some examples of ones that are already built. Most government agencies have some. The ones in Europe, you need to license. The ones in the US are normally free for download, but you should sign up for the updates. There are also, I just mentioned Taxobank. There are a lot of places where you can license vocabularies from around the world. Knowledge domains are taxonomies or thesauri or authority files that are already built. They have full-term records, so they have that thing I showed you on the right-hand side of a screen a bit ago with the hierarchical equivalence and associative relationships and all the other kinds of notes and codes and stuff that are available. And all of them are compliant with both the NISO and the ISO standards. The export formats are many, everything from Excel or CSV to SCOS. In our case, we have 4 different flavors of the knowledge organization system exports. We also have OWL exports and MARC exports, about 22 of them altogether, lots of XML, HTML, and so forth. There are general purpose taxonomies, and this is an example of some of the topical areas, and you can see that they are very diverse. Excuse me. There are some that are available as primarily SCOS downloads from different organizations. Most of whom are willing to share them so that you'll talk the same language that they do, using the same information for tagging. There are others that are updated so frequently that they're better made available as a software as a service kind of situation. And those include things like the international classifications of diseases, both the ICD-10 and the ICD-11, which is used for medical coding. When you get that thing, as you check out, you see a bunch of little numbers when you check out from the doctor, and that's the ICD codes. So every ailment that you have that's being reimbursed via insurance has certainly had an ICD code attached to it. There are also things like the Royal Botanical Gardens at Kew has a medicinal plant name system. It has an average of 17 synonyms, whereas Taxogene down there at the bottom, based on the human genome, has an average of 19 synonyms. So for just structural integrity and publishing integrity, it's really nice to have use the proper name instead of all those synonyms and have them automatically identified by a taxonomy or a filtering system. A lot of people talk about knowledge graphs, and that's a structured representation of knowledge. Over here, we have Google's knowledge graph on the side, and they talk about things a little differently than taxonomies and thesauri and controlled vocabularies, in that each node, which might be a concept or a term or an entity, is called a node, and the edges are the relationships represented by those arrows between the different entities or concepts. They use other kinds of semantic and linked data principles and technologies and integrate information from many sources so that people can look for and find new knowledge based on connections that they didn't know were there until they loaded the data together so that they could see it. Those data and its relationships allow some very precise querying and analysis, and that discovery process of those connections and patterns in the data are sometimes very surprising and very helpful. They are used for organizing and navigating great big amounts of data, and so that we can generate new knowledge as well as get new insights. I know that all of you have used knowledge graphs or seen knowledge graphs. If you go to Google Maps, for example, or you go on Google, depending on the amount of information that Google has available, it'll display a new knowledge graph. So the one on the right is one of Harrison Ford's age, he's 77, and it gives people who have been similar to him or related to him in some way and their ages. Over here on the left, we see one about Clint Eastwood, and it brings in, and if I were to scroll down, a whole lot of information linked and displayed in a very pleasing manner using a knowledge graph behind the scenes, that little node graph that I showed you with the yellow blobs in the previous screen. So those are increasingly popular, and they are definitely knowledge graphs. So a knowledge graph can use a controlled vocabulary so that it's consistent, interoperable, it uses the synonyms with semantic enrichment, and gives good domain understanding. So they are linked. If you are building a knowledge graph, you almost always have to build a controlled vocabulary first. Knowledge graphs within generative AI have a little bit more background needed. They're contextual in their understanding. They provide the relationships between those entities and concepts, as we discussed earlier when we were talking about how the relationships and taxonomies work, or thesauri work. And it gives you more relevant and contextually appropriate responses. It also helps with the content generation. It's faster and more reliable if you're using that tagged data to generate the knowledge graph out of the generative AI system. They can also be used in the training to generate more coherent and accurate outputs, and ensure that the generated documents adhere to the domain's principles and conventions, because as I mentioned earlier, different people talk about things in different ways. And if you want to be within a particular group's thought patterns, methodologies, and theories, then you need to use a system that'll support that in the background. For entity linking and disambiguation, it's important to be able to disambiguate things like Mercury, as I mentioned earlier, or things that have a lot of different ways to say things, like a couch and a Davenport and a settee and a sofa. You want to get those linked together, and it's much faster in the model if those have already been organized for you. If you can link those, then those entities do not repeat, but they show once, and gives you much better insights and reduces ambiguity in the graph. You can also use them for personalization, and particularly if you have some definite points of view on how that should be working. So how do we link them? Putting a knowledge graph into a generative AI system. So we've got the controlled vocabulary, we've built a knowledge graph, now we're going to link it in. Well, first we have to define the schema, defining those entities and relationships and properties. A lot of those already exist. It's nice to be alive in 2024 because so much of this stuff has already been written. And then you acquire, of course, and process the data, same as we outlined earlier, and use whatever is the suitable format for loading it to your knowledge graph software. There are a number of different graph softwares out there to use. And then you populate it and load it into the knowledge graph, and you get an idea of what the data will look like. You need to ensure as you go that your entities are representative as nodes, the relationships as edges, and the properties as attributes when you get them loaded, because sometimes they get misidentified. Then once you've got the knowledge graph, you want to incorporate it into a model for the training purposes so that you can display the data that you've dumped into generative AI. And you can use that graph to access and utilize the structured knowledge that's represented in the graph. The training and fine tuning happens over and over and over again. Supervised learning with labeled data is very effective, but unsupervised learning you also want to have so that you can discover other patterns and relationships within the data. And of course, you use it to generate output or answers to user queries, and you have to continually iterate. It's not a one and done kind of process. Okay, let's talk about ontologies for a second. I know it's a lot of slides, Bill. So an ontology is a formal and explicit specification of conceptualization, defines the terms, concepts, and relationships within a particular domain of knowledge. And I always found that to be a confusing definition. So it's a formal framework. They have terms or concepts, which we've already talked about, whether they're entities or classes, as they're called in ontologies, or categories within some subject domain. Each term or concept or entity has to be defined with a precise meaning, same as you do in the thesaurus. And the relationships are going to define the connections between the terms, and they can represent all kinds of relationships. They can be hierarchical, broad and narrower terms, whole parts, associative, meaning related terms. They also have some room for synonymy. And then it also needs to represent whatever the constraints are, things that you want to define as the behavior of the terms and the relationships. And that's where you are defining your predicates, and it becomes very confusing. Ontology usually or often uses RDF, which is the resource description framework. People say it's an RDF file. Well, RDF, it's at its very simplest, is just defining itself either by reference or inclusion of the schema that defines what the tags and labels and how they interact are. So it can say, go to this website and see this HTML4 definition, or it can say, here's the schema at the top of the file. Either way works. We talk about a subject or a research source, which is a thing that has a relationship, which is the predicate or the edge, which another thing with another thing known as the object or the resource. So a thing can work together with something known as a predicate. And when people talk about subject, object, predicate, it's interesting that both the subject and the object can be the same thing. So we need to understand the interoperability of those things because they play different roles depending on where they are in the statement or the triple. But one thing that, well, the reason for ontologies in general is the interoperability and reasoning and semantic understanding that is allowed across different systems and applications. They do connect things, not strings of data. So I think this is my last definition, which is tagging or indexing. So in the library science world, library and information science, they call indexing the tagging process. In computer science, indexing is thought about as the creation of an inverted file or a key index, not meaning the same thing at all. But for my purposes today, I want to talk about tagging and indexing as the same definition. And it's where we've taken that keyword, that taxonomy term, that subject heading, and we're applying it to the text. So whether it's things like people, places, objects, entities, or concepts, we are going to tag those to the content itself. Okay, deep breath. 20 minutes to go. Natural language processing and machine learning and AI are not new. We've been trying to automate human activity for 200 and some years. One of the big things that happened leading to industrial revolution was the mechanical automation of weaving, for example, the jacquard looms. And from those looms and the way the cards work to get the jacquard designs, a guy named Herman Hollerith in 1890 got the contract for doing the US Census, and he did it on punch cards and finished the tabulation in 3 months instead of several years. A few years later, the Thomas Watson Group, forming IBM in the 1920s, took up those Hollerith cards, also known as punch cards, and pictured here. We have a lot of them at my house because my husband still uses them for note cards. And so automation using computers began quite a while ago. In 1957, in October, Sputnik took off, and the Russians were suddenly way ahead of us, and the Western world, Europe and the US, suddenly became aware of what was happening, and it led to both the space race and the Cold War. In reaction to that, a whole lot of really basic research took place. One of my favorites was in 1964, the Council on Scientific and Technical Information was convened at Oak Ridge under a guy named Alvin Weinberg. And they produced this incredible report, which I commend to all of you, the Casati report. And a lot of the things that they outlined there still have not happened. But the basic thinking is there and very sound. That led to the creation of one of the first really big thesauri, the Thesaurus of Scientific Engineering, Scientific and Technical Terms, and which was broadly used for almost all of the big research agencies of the US and of Europe for quite a long time, and derivatives still exist in NASA and DOE and Defense and European Space Agency and other organizations. The automated retrieval of documents, because there were so many of them, it was such a big avalanche of information, led to the development of systems like the NASA Recon system, and then later the dialogue system, and finally ARPA and DARPA and the internet. But the basic algorithms are even older. George Boole, of Boolean algebra, lived 1815 to 1864. And certainly those thoughts that he had are basic to the design of computer circuits. And Bayes, father of the Bayesian algorithms that talk about probability of an event happening based on what happened before, forms both the basis of a lot of computer science, but also of the legal field, because probability or beyond reasonable doubt is a case often used in legal nomenclature. So this is a long building process that we've had. The AI building blocks from natural language processing, Alan Turing and his original article on computing, machinery, and intelligence is a landmark paper published in 1940, and Jabberwocky was one of the early chat boxes formed in 1997. We also had along the same times a lot of machine translation, automated translation activities like Sistran and the English-Russian translation systems and others. Rule-based approaches became very popular in the 1990s, and the World Wide Web not that many years ago with HTML. Along the way, we also had development of vectors and engrams, and I said I wasn't going to talk a lot about the technology, and I shouldn't, but it's amazing how much is there. What's curious is what's the big deal all of a sudden now? Why is suddenly AI taking everything by storm and so possible when it wasn't just a few years ago or even months? Well, it's the power and the size of the computers that we have. We have more power and more size in my cell phone than we've ever had at our fingertips before. It's just incredible. So all the things that we thought maybe would be possible are now possible because we have both the bandwidth and the storage and processing capacity. So AI, we start with that tag enriched content. We're going to feed it to a Gen AI system. Gen AI has its own rules, and it puts those rules into its inference engine, and search get better and better and better. And we add more data, and it retrains, and it can train quickly because the computers are big and parallel. And so we have these fabulous things, but there are some drawbacks. Like, for example, there was an experiment at MITRE, MIT's offshoot, to identify cancerous skin lesions, and it came back 100% accurate. And they were really thrilled until someone realized that every time you looked at a skin lesion like this, there was a bar. And only cancerous lesions had something measured. The ones that were not cancerous or were not identified as cancerous did not have a bar. And so what the AI was training on was the bar and not the picture of the lesion itself. And so we have to be really careful and really aware of what kinds of things are being measured by the system, because that wasn't immediately obvious to anyone. Excuse me. There are some things that we need to be aware of also. ChatGPT did a data cutoff 2 years ago. Took a lot of manpower, people in Nigeria getting paid a lot for them, not much from our point of view, to train the model. And they constantly trained and retrained it, but now that it's out and available, who's training it? What kind of system can we use that'll enhance that data and lead to new information from existing data sets? Well, there are some new ones, like this one out of Microsoft, GLAN, which is a general instruction tuning system, which breaks knowledge into domains and subfields and disciplines. It's a taxonomy divided by branch or a syllabus for each subjects. And it produces something very similar to the human educational system or a curriculum outline, like the National Information Center for Educational Media Knowledge Domain. It's flexible, it provides lots of instructions on an enormous scale, and it doesn't care what the task is. It adds lots of fields and skills, and it's very helpful to people. So you can add and train new domains and add a new node to its taxonomy every time you turn around. Another one is Baseline, also called, I don't know how to pronounce that word, which deals with chat boxes, and the systems were flooding the system. They were just flooding the system with lots of information, and the responses were becoming irrelevant and not very precise. So in fine-tuning the system, what they did was add words from a taxonomy as an incoming filter, and then they could tune the responses so that people were able to get better responses, and they could do constant updates and additions based on the interaction logs. So this is how it works, and it's interesting to see the model itself. But what's important is up top, we see that keywords are an incredibly important part of training this model. So we need to think about how those models are trained and used and work together, and that the addition of keywords, controlled vocabularies, are very helpful to ensuring that you don't have a huge mess on your hands from too many things overpowering the system. So it's the technology is a tool. It's not the focus. In order to implement it, you might need a shiny new piece of technology, but it's part of the chorus. It's not the main character. And most companies want to lead with the technology, and they don't spend much time understanding their users or aligning their strategies. You'll find that most companies, big ones, have thousands of SharePoint or Teams sites where people still can't find the information that they want. Most large corporations have at least 5 software systems on the shelf that don't work, and they try another one and another one and another one, and none of them work because the data was not enriched in the first place. If they look at the data modeling first and organize the data so that it's clean and enriched, they'll get a much better experience. But if they ignore the data, they face a failure again. It doesn't usually work in a 2-week sprint. It's going to take more like 3 months. But if you can get the executives to agree on a strategy and stand behind you, then you can structure the model into a coherence model, governance pipeline, and resourcing, so that you know how you're going to handle all the data from the get-go, and then you have a very successful system. But without it, there's no strategic value to an AI initiative over any of the other initiatives that people have before. They won't work. It's the data, or it's the data stupid, like it's the economy stupid. The data is the core asset. The content is what people are trying to find. The content is what people are trying to organize. And without the data, the rest of the initiative is nothing. So it's an essential component of the strategy. And if you enrich the data first, particularly with subject metadata, taxonomies, ontologies, or other models, you have a much, much better experience. The large language models not only mirror, but magnify the problems with data sets. And you don't realize you have those problems until too late. So pay attention to the data. Taxonomy or thesaurus is going to match your content. It scales with the content increases. It's an extensive synonymy, or should be. It'll disambiguate things like mercury, but also LEAD, which could be lead or lead, and make it much easier for people to build in feedback loops to keep current with their content. It also prevents hallucinations, because the misunderstandings of multiple word meanings, that disambiguation or nonsensical output. The model that is not trained on your content will have factual contradictions, because people in different areas talk about things differently. And sometimes the query will go against the rules of the system because you didn't have it organized in the first place, and that gives you prompt contradictions. So in order to get rid of all of those problems, we want to index and tag the data sets. When you use recommendation index using tag sets and not just vectors, you get a much higher accuracy level. If you do it automatically, you get sub-second versus 70 seconds per tag. If you're manually tagging, you get always the most specific level of the tagging, no misspellings. You have consistency, no editorial drift, where people use the same tags over and over and over because they're used to them. And you don't need as many subject experts, and it's replicable. It's not a black box. So, I'm running slow today. So we're going to dump our data into the vortex. We could use a hybrid approach. We could use ChatGPT to tag our data. It could build the taxonomy. It could organize the information, extract it, and read the answers from that Gen AI system. You have to submit it several times, and the answer might change every time, but that's because you added new data to it. And you can send the same query to your own content using the same terms that you used in the ChatGPT. and use that to tag the data. The advantage to this is it keeps your data out of the large language model. And you combine the two to get a quick summary of the material at the end. So that's the first approach. Second approach, which I call bludgeon your data, is to gather a large amount of text, license the Gen AI of your system, convert it, load it, train it, ask a series of refining questions. Notice there's no taxonomy in this system. Summarize, classify, and display it using AI to make the classification model for your own data. And the third way is where you have taxonomy priority or in semantic enrichment, where you organize and enrich the data first, and then you train it. I've already gone over how you do the taxonomy development, so I'm not going to go into that. And I also went over how you gather and clean the information. I didn't talk about extracting the entities, which you can. You can do the same kind of disambiguation on entities, which are called many, many different names. I'm Margie Lava, Marjorie Lava, Marjorie MK Lava, M Lava, and so forth. And so if you want all of those collapsed into one entity for search, you need to do the same kind of thing that you do in taxonomy development. And then you integrate the taxonomy at the end. So how do taxonomies help with large language models? Well, they help in understanding the input and organizing the content, in representing the knowledge, also in query expansion. So you can go from a broader term to its narrower terms, or from the narrower term to the broader ones. You can also go across hierarchies with related terms, and you can find all the synonyms and get them all in there together. It also provides a yardstick for quality control. So do they make it behave? Well, they help with decision making. They enhance the understanding. They improve the consistency. They facilitate interpretability, meaning not interoperability, but interpretability, so that you understand what the word means in the context, and also in supporting compliance, which is a legal construct that many of you will have to deal with in making sure that the data conforms to the rules and regulations of whatever industry you're in. And that's it. I didn't leave as much time for questions as I thought I would. It's 2 minutes to the hour. So back to you, Bill.
Well, we've got a question from Barbara that's actually one of the two questions I had for you. So at least two of us are asking the same question, which is the scalability of this. Like, I'll summarize Barbara's question can this be done on a small scale? In other words, my perception is to actually create a knowledge graph. It's a giant project. You need an expensive system like MarkLogic or something like that under the hood, et cetera. To what extent is it possible for a smaller organization to do some of this stuff without having the budget that an AACR maybe has?
So that's the advantage to using the existing taxonomies. There it is.
Your knowledge domains that you're talking about.
Right, the knowledge domains. So if you license one of those or download a free one from a government agency, then you don't have to create the knowledge graph. You can adapt it by running it against your content, and wherever the terms actually apply, keep those terms and throw out the rest of them. So if the terms are not used, there's no content to match them. There's no sense keeping them in your taxonomy over time.
Great. And my understanding is that you at Access Innovations, you've got a whole bunch of these available knowledge domains. Can you just give us a sense of order of magnitude? How many different kinds of things do you have?
We have about 80 of them that are available with automatic indexing so that they can be automatically applied. That means they have a rule base already made. There are about 2,500 of them that we have listed in Taxobank that are available. So they cover the waterfront in terms of domains, which are not necessarily already made to automatically apply to your content, but that happens very quickly because 80% of the terms, particularly with a rich synonymy, already would work in an automated or auto categorization or auto indexing system, such as the Data Harmony MAI. So yeah, there's a lot of them already available. That they're certainly for some areas we need to make a bespoke or custom taxonomy, but in most cases these days you start with one that already exists and then tailor it to the individual organization's content.
Great, that makes a whole lot of sense. Well, I think we're out of time, but we've only had that one question, and I had two, but the other one is pretty detailed, so I guess I'll we can wrap it up.
And if
we're
anybody
a couple minutes over here
wants a copy of these slides or wants to talk further, my information is available on that slide I just stopped sharing.
Yeah, and just Google Access Innovations and you'll find Margie, right?
That's right. Or my name, Marjorie Lava, is pretty unique in the business.
Yeah. Okay, well, thanks everybody. I hope you found this informative. I sure did. You really covered a lot of ground really well, Margie. Thank you so much.
You bet. My pleasure. Thank you, everybody.